Good morning, everybody. Today we will discuss about approximate method for calculating heat transfer on a heated flat plate. Now, this approximate method is based on momentum integral and energy integral method. We will take it up, but before that let us look at this picture where we can see formation of hydrodynamic boundary layer, velocity, that is velocity boundary layer, and temperature boundary layer, which is thermal boundary layer, for the cases of Prandtl number less than 1 and Prandtl number greater than 1, and depending on Prandtl number less than 1 or Prandtl number greater than 1, we know that delta and delta T are related. If Prandtl number is greater than 1, delta by delta T, that is velocity boundary layer divided by thermal boundary layer, two boundary layer ratios are proportional to Prandtl number to the power 1/3. And if Prandtl number less than 1, then delta by delta T is proportional to Prandtl number to the power half. So this is the basic consideration. We can see the, as I said, growth of velocity boundary layer and thermal boundary layer on the flat plate, which is heated at a constant temperature Tw. So the governing equations are continuity equation. We can see del u del x plus del v del y equal to 0. Velocity boundary layer equation, u del x plus v del y equal to minus 1 by rho dp dx plus nu del 2u del y2. And thermal boundary layer equation, this also we have derived, u del t del x plus v del t del y equal to k by rho cp del 2t del y2. Now the boundary conditions are at y equal to 0, u equal to 0 and v equal to 0. This is no slip boundary condition at y equal to 0, u equal to 0, and impervious boundary condition is at y equal to 0, v equal to 0. So since this is solid wall, both the conditions are applicable. At y equal to 0, I have used this symbol at the rate, but this means at. And at y equal to 0, t equal to t infinity. At y equal to delta, that means edge of the velocity boundary layer, u equal to u infinity, and at y equal to delta t, at the edge of thermal boundary layer, t equal to t infinity. At the wall, y equal to 0, thermal condition is t equal to tw, and at y equal to delta, t equal to t infinity. Now, integral method was basically proposed by von Karman and Paulhausen. So this is often called Karman-Paulhausen method. And this is basically integrating the boundary layer equation within the thickness of the boundary layer. That means we can write here this boundary layer equation. We can write 0 to delta integration u del x dy plus again integration 0 to delta v del u del y dy equal to 0 to delta integration minus 1 by rho dp dx dy plus again 0 to delta integration nu del 2u del y2 dy. This we can call, just we locally define this as term 1, this as term 2, term 3 and term 4. Now term 3 is 0 because for flow over a flat plate we know that dp dx is 0. So the third integration or third term we can dispense with, since it is flow over a flat plate, 0 pressure gradient surface. Otherwise, if it's a curved surface, we will have dp dx accordingly. So here we are neglecting dp dx, and the second term is basically, you can see this is v del u del y dy. Now and integration 0 to delta. So this is basically the we can integrate by applying integration by parts. So first function into integration of second function, then we apply the limit minus derivative of the first function into integration of the second function, then entire thing integrated between 0 to delta. So what from here we can write u into v at delta upper limit minus u into v at 0 plus this is 0 to delta. By applying integration of parts we got del v del y into u, entire thing into dy, but we can substitute now del v del y by del u del x. So 0 to delta u del u del x dy, that comes from continuity equation. Continuity equation is del u del x plus del v del y equal to 0. So del v del y is minus del u del x. So this becomes plus, we can write plus 0 to delta u del u del x dy. Now this part has to be evaluated. So we can write again del u del x equal to minus del v del y. So del v del y integration between 0 to delta dy is minus 0 to delta del u del x into dy. Now this integral, that means del v del y into dy, result of which is v at y equal to delta minus y equal to 0. V at y equal to 0 we know 0, but v at y equal to delta becomes then minus integration 0 to delta del u del x dy. So in the previous page, this integral second term is basically we got uv at delta minus uv at 0. U into v at 0, u is 0, v is 0, u into uv 0 is 0, but uv at delta is non-zero, plus from here we got u del u del x dy integrated between 0 to delta. Here when we evaluate this, we get then v at y equal to delta is given by this expression, and u at y equal to delta is u infinity. So we can write minus u infinity 0 to delta del u del x dy is basically u into v at y equal to delta. So this term basically u into v at y equal to delta, and then we had this term, so we can write minus u infinity integration of del u del x dy between 0 and delta plus integration of u del u del x dy between integration between 0 and delta. So this equation now we have got, basically what the meaning of this term. This term remains as is. This term is 0, and on the right hand side, if we integrate, we will get nu del u del y at y equal to delta. So at y equal to delta minus y equal to 0. So nu del u del y at y equal to delta, since del u del y at y equal to delta vanishes, so that will not produce any term, but the lower limit, that means minus nu del u del y at y equal to 0, will be there. As such, that is basically shear stress by rho. So now combining all the terms, we get twice 0 to delta u del u del x dy minus u infinity integration 0 to delta del u del x dy equal to minus what we said, nu del u del y at y equal to 0. Mu del u del y at y equal to 0 is shear stress divided by rho, because we have nu. So this is a term which means shear stress by rho. But we are writing nu del u del y at y equal to 0. So this equation we can rewrite as ddx of 0 to delta u square dy from here minus u infinity, again ddx integration 0 to delta u dy, we can clearly write from this term, equal to minus nu del u del y at y equal to 0. Now you can see one operation, that is the differentiation which was within the integral sign, that differentiation, that operator has been taken out, and we have written ddx of 0 to delta u square dy. So basically we apply Leibniz rule to evaluate basically differentiation under the sign of integration. So 2 into twice 0 to delta integration u del x dy, we can write as ddx, and this is no longer partial derivative, this is ordinary derivative, 0 to delta integration u square dy. Same Leibniz rule can be applied here, that is u infinity ddx of ddx, and inside we can write integration 0 to delta u dy equal to minus nu del u del y at y equal to 0. This is basically momentum integral equation for a surface where dp dx is 0. For zero pressure gradient surface, or flat plate, we write this equation which is momentum integral equation. Now, in order to solve the momentum integral equation, we take a velocity profile which is given by C0 plus C1y plus C2y square plus C3y cube, a third order polynomial. This is expression for u. Now, again, based on our basic philosophy, if we express non-dimensional u, that is u by uppercase U infinity, equal to, then y will be divided by delta. We will express both the sides in such a way that it will describe a similarity velocity profile. So u by U infinity equal to C0 plus C1 into eta plus C2 into eta square plus C3 eta cube. Eta is called similarity parameter. Despite the growth of boundary layer in x direction, u by U infinity remains similar for same y by delta at any x. This is the basic philosophy of finding out similarity variables for flow over a flat plate. Now we apply the boundary conditions. At y equal to 0, u equal to 0, we know this is no slip condition, or at eta equal to 0, u by U infinity equal to 0. If we apply that, clearly we get at eta equal to 0, u by U infinity 0, C0 is 0. Next we apply, we will come to this, although we have written the second boundary condition here, but this will apply next. After applying this boundary condition, we will go to this boundary condition, which is again at y equal to 0. Y equal to 0, if we consider the boundary layer equation, in boundary layer equation u equal to 0, v equal to 0 for y equal to 0. So we get del 2u, del y2 equal to 0. This is a derived boundary condition. So del 2u, del y2 equal to 0. That means at eta equal to 0, del 2 del eta 2 of u by U infinity is 0. And if we apply that, then we will differentiate this twice. So twice C2 plus 6 C3 eta at eta equal to 0 is 0. So this means at eta equal to 0, if we substitute for eta equal to 0, then we'll get C2 is 0. So in this expression, C0 is 0, C2 is 0. So we are left with C1 eta plus C3 eta cube. Then we apply at y equal to delta, u equal to U infinity. That means at y equal to delta means eta equal to 1. It's the edge of the boundary layer, y by delta. So when y is delta, eta is 1. Then u by U infinity, velocity profile also reaches the value of 1. U becomes equal to U infinity. So C1 eta plus C3 eta cube at eta equal to 1 is 1. That means C1 plus C3 equal to 1. Similarly, at y again, so we have already applied this, found C2 equal to 0. Then we go for the remaining boundary condition that at y equal to delta, del u del y is 0. The velocity gradient becomes 0. U becomes equal to U infinity, and there onwards from the edge of the boundary layer to rest of the flow field in y direction, we can apply del u del y equal to 0. So at eta equal to 1, then del eta of u by u infinity equal to 0. That means we can differentiate these ones. Del eta of u by u infinity. So we get C1 plus C3, 3C3 eta square at eta equal to 1, 0, which gives us C1 plus thrice C3 equal to 0. So we get C1 plus thrice C3 equal to 0 and C1 plus C3 equal to 1. So these two we solve for C1 and C3. And then we get C1 equal to 3 by 2, C3 equal to minus half. So in our velocity profile, u by u infinity, C naught is 0. We get the value of C1, 3 by 2. C2 is 0. We get the value of C3 minus half. So it becomes 3 by 2 eta minus half eta cube. So we get u by u infinity 3 by 2 eta minus half eta cube. Now, if we recall our momentum integral equation, in the momentum integral equation now u is very explicitly known, so we can evaluate term by term momentum integral equation, equation 4. So what we do, we first evaluate integration 0 to delta u square dy, u by u infinity we know, so u square we substitute and perform the integral. Dy means y by delta is eta, dy means delta d eta. So we perform this integral and we get basically this result. After integrating this, that means basically 9 into eta cube by 3 plus eta to the power 7 by 7 minus 6 into 5 eta to the power 5 by 5, and then we substitute, we replace the value of eta or substitute the value of eta by 1 and for the upper limit and for the lower limit 0. So we get this, and finally we get this equation. So we integrate this profile, which gives, as I said, 9 eta cube by 3 plus eta 7 by 7 minus 6 eta 5 by 5. And then we put the limit eta equal to 1 and 0, get this integration. Similarly, integral associated with the second term, 0 to delta u dy. So this will be then u infinity by 2, 0 integration 0 to 1, 3 eta minus eta cube. 2 comes out, 3 eta minus eta cube delta d eta. So we get 5 by 4 u infinity delta by 2. Then the right hand side is minus nu del u del y at y equal to 0. So minus nu del u del y means del eta, del eta when we express del u del y, then it becomes del this whole quantity by delta del eta. So, and after derivation, after finding out the derivative, we substitute eta equal to 0, it becomes minus 3 by 2 nu u infinity by delta. So right hand side is also evaluated. Left hand side we had these two integrals, those have been evaluated. And now if we plug in those, we get u infinity square by 4 ddx of delta within bracket 68 divided by 35 minus 5 by 2 equal to minus 3 by 2 u infinity nu by delta. So from here we get basically delta we transfer to this left hand side from right hand side. So delta d delta dx equal to this also result we transfer to from left hand side to right hand side. So 140 by 13 u nu by u infinity. This u infinity square comes to the right hand side from here. So we get delta d delta dx equal to 140 by 13 nu by u infinity. On integration, we get basically this will give delta square by 2 and 13 by 140 we transfer to left hand side. So half 13 by 140 delta square equal to nu x by u infinity plus integration constant c. Now we can apply the boundary condition that at the leading edge, that means at x equal to 0, delta equal to 0, which will give c equal to 0. So from here we can write delta square is 280 by 13 nu x by u infinity, which finally gives delta equal to 4.64 root over nu x by u infinity. And we know Reynolds number at any x from the leading edge given by u infinity x by nu. So this we can rewrite as delta equal to 4.64 into x by root over rex. Now compare this with the exact solution that we got from the series solution of Blasius. There we got delta equal to 5x by root over rex. Here instead we are getting 4.64x divided by root over rex. So, and we know this is approximate solution. So approximate solution is not really much different than the exact solution. Exact solution was delta equal to 5 into x divided by root over rex, and here we get delta equal to 4.64x divided by root over rex. So now having solved the velocity boundary layer, we take up thermal boundary layer equation. And in the thermal boundary layer equation, again we integrate term by term within the thermal boundary layer. That means every term is integrated with respect to dy within the thermal boundary layer from 0 to delta t. So integral 0 to delta t u del t del x dy. This was u first term. Second term will be again integral 0 to delta t v del t del y dy equal to right hand side k by rho cp del to t del y2 integrated between 0 and delta t dy. So first term we retain as such. Again second term we integrate applying integration by parts. So this becomes first term into integration of second term. We apply the limits minus basically derivative of the first term del v del y, integration of the second term, and together it is integrated between the limit. equal to K by rho Cp del T del Y at delta T and upper limit and lower limit 0. So 0 to delta T U del T del X dy, we retain it. This term at the edge of thermal boundary layer, T becomes T infinity. So this term we have written here, just we have changed the location. So basically at the edge of boundary layer, T is T infinity, then V at delta T. And lower limit, V is 0, so will not have any value. This is the upper limit. And V at delta T, from continuity equation we can write minus integration 0 to delta T del U del X dy. So we will substitute that later. Then, so this, when we integrated this integration by parts, we got this term is evaluated this way. And the second term, which was basically derivative of V, integration of this term, and the entire term is again integrated, between 0 to delta T. Here we simply substitute del V del Y by del U del X. So this minus sign becomes plus 0 to delta T, T del U del X dy. So these two terms we have written equal to minus K by rho Cp del T del Y. Del T del Y, again the temperature profile at the edge of boundary layer, it becomes del T del such that del T del Y is 0. So when we apply upper limit, we don't get any result, but lower limit, this is a very meaningful term. We will see this indicates basically heat transfer. So this is minus K rho Cp del T del Y at Y equal to 0. And then again, as I said, here we did not substitute V at delta T. It is given by minus 0 to delta T del U del X dy. So if we substitute V as this term minus integration between 0 and delta T del U del X dy, then these first three terms we can combine as integration 0 to delta T U del T del X plus T del U del X dy minus T infinity 0 to delta T del U del X dy. So first three terms can be rearranged in this way. And this is equal to minus K by rho Cp del T del Y at Y equal to 0. So this integral we can now write as these three terms we can put together as del X of U into T minus T infinity. Del X of within the square bracket U into T minus T infinity. And this entire term integrated with respect to dy between 0 to delta T equal to minus K by rho Cp del T del Y at Y equal to 0. And again we apply Leibniz rule, which is differentiation under the sign of integration, and we write ddx of the entire quantity under integration sign 0 to delta T U T minus T infinity dy equal to minus K by rho Cp del T del Y at Y equal to 0. And this equation is known as energy integral equation. So energy integral equation, again, in order to evaluate the energy integral equation, we require velocity profile and temperature profile both. Velocity profile we have already found out. Now we have to find out temperature profile. So temperature profile, here we define theta as T minus TW divided by T infinity minus TW. Our conventional way is T minus T infinity divided by TW minus T infinity. We have changed it slightly. We have written T minus TW divided by T infinity minus TW. And we have taken up this profile. This is C naught, C1 xi plus C2 xi square, C3 xi cube. This is also higher order polynomial, third order, and xi is the similarity variable for temperature given by y, given as y by delta t. So now again we apply the boundary condition in order to evaluate this constant so that we can get the complete profile. Now at y equal to 0, we know T equal to TW, wall temperature. So if we substitute that, that means at xi equal to 0, because y equal to 0 means xi equal to 0, at xi equal to 0, then theta becomes 0, which is, basically, which gives directly C0 equal to 0. Then at y equal to 0, del 2t del y2 equal to 0. This is again from the governing equation. U del t del x plus v del t del y equal to k by rho Cp del 2t del y2. Since u and v on the plate is 0, so at y equal to 0, we can write del 2t del y2 equal to 0. That means at xi equal to 0, del 2 theta, there is a mistake, this should be d xi2. Please correct it. Del 2 d2 theta, this should be d xi2. It is not eta. This should be d xi2 equal to 0. So if we differentiate with respect to xi twice, we will, and set it equal to 0, we will get C2 equal to 0. So C0 equal to 0, C2 equal to 0. Then we apply the third boundary condition at y equal to delta, again t equal to t infinity. So that means at y equal to delta means at xi equal to 1, t equal to t infinity means theta equal to 1. So at xi equal to 1, theta equal to 1. Already we have seen C0 and C2, these are 0. So from this expression, we will get C1 plus C3 equal to 1. And then again y equal to delta t, that means edge of boundary layer, dt dy is 0. That means at xi equal to 1, this term should be read as d theta d xi, not d theta d eta. Please correct this also. This is also a typographical mistake. So this is d theta d xi equal to 0. So d theta d xi, if we find out from this expression, just differentiate once, knowing C0 and C2 are 0, we will get C1 plus thrice C3 zeta square, and then we set zeta equal to 1. So C1 plus thrice C3 equal to 0. Let me repeat. This is at y equal to delta t, del t del y equal to 0. Y equal to delta t means xi equal to 1. At xi equal to 1, if we differentiate this with respect to xi once, C0 is not there, C2 is not there, we'll get C1 plus thrice C3 xi square. And for xi equal to 1, that means it is C1 plus thrice C3, and that is equal to, basically we have said that d theta d xi equal to 0. So that is d theta d xi is C1 plus 3 C3 xi square, that is equal to 0. So C1 plus thrice C3 equal to 0. So we have to solve these two. C1 plus C3 equal to 1, C1 plus thrice C3 equal to 0. Solving, we get C1 equal to 3 by 2 and C3 equal to minus half. So this profile T minus TW divided by TW minus T infinity minus TW, T minus TW divided by T infinity minus TW, this becomes 3 by 2 xi minus half xi cube. Almost it is analogous to the velocity profile. And we then evaluate theta minus 1. Theta minus 1 means T minus TW divided by T infinity minus TW minus 1, which gives this, equal to then T minus T infinity divided by T infinity minus TW. From where we get T minus T infinity equal to theta minus 1 into T infinity minus TW. This is just, we find out the expression for T minus T infinity for ease of our operations. So now we look at this energy integral equation, U into T minus T infinity. That is the reason we found out an expression for T minus T infinity. So T minus T infinity is this. U already we know, we have obtained U by U infinity as 3 by 2 eta minus half eta cube while solving the momentum integral equation. So the left hand side of energy integral equation, now we can write T infinity minus TW into ddx of integration 0 to delta t u into theta minus 1 dy. So this is this left hand side we can write now as this. And then we basically substitute u by u infinity, which is 3 by 2 eta minus half eta cube, and infinity we bring here, and this is theta minus 1, and we have seen theta is given by this, and theta minus 1 means this 3 by 2 xi minus half xi cube minus 1. 3 by 2 xi minus half xi cube minus 1 dy. We perform this integration u infinity t infinity minus tw ddx of the entire integral, and integration is between 0 to delta t, 3 by 2, this is nothing but y by delta minus half y by delta cube multiplied by 3 by 2, this is xi y by delta t minus half y by delta t cube minus 1 dy. And we evaluate this integral, only thing, and then we substitute the upper limit and the lower limit, and we get this expression. And in this expression we have introduced another new variable, which is zeta. And zeta is nothing but delta t by delta. After integration and substituting the upper limit, we'll get this delta t by delta term, resultant or in the final expression. So, and we have written it also in this way: ddx of delta within the curly bracket 3 by 4 zeta square minus 3 by 20 zeta 4 minus 3 by 20 zeta square plus 1 by 28 zeta 4 minus 3 by 4 zeta square plus 18 zeta 4. And after further simplification, we can write u infinity t infinity minus tw ddx of within square bracket delta into within curly bracket minus 3 by 20 zeta square plus 3 by 280 zeta 4. So this is a left hand side evaluation of energy integral equation. Similarly, again we write the full expression for t minus t infinity, which is t infinity t minus tw, which is t infinity minus tw into 3 by 2 multiplied by y by delta t minus half y by delta t cube. From here we find out del t del y, and we finally write the right hand side minus k by rho cp del t del y at y equal to 0. We get it as minus alpha thermal diffusivity 3 by 2 t infinity minus tw by delta t. So basically y equal to 0, this term is knocked out. So we get this expression on the for the right hand side term. Now equation 8 becomes t infinity minus tw into u infinity ddx of this we got in the previous page, ddx of this quantity. So we write ddx of delta into minus 3 by 20 basically zeta square plus 3 by 280 zeta 4 equal to minus 3 by 2 alpha t infinity minus tw by delta t. Now if we consider Prandtl number greater than 1, that means delta is greater than delta t, and zeta was basically delta t by delta. So Prandtl number greater than 1 means delta t is less than delta. So if delta t is less than delta, zeta is less than 1. And zeta 4 has to be much less than zeta square, right? When delta t is less than delta. That means when delta is greater than delta t or Prandtl number is greater than 1. We can invoke this simplification that zeta power 4 is much less than zeta square. So this term can be dropped. So basically these are the ways of simplification, and we can also mention here that such simplifications will not alter the final result, because these are very reasonable simplifications. So this is a situation when Prandtl number less than 1, and this is a situation when Prandtl number greater than 1. Prandtl number greater than 1 means delta is greater than delta t. Prandtl number less than 1 means delta is less than delta t. So with Prandtl number greater than 1, then this equation 10 which we have written, we can drop this term and we can write delta u infinity ddx of delta into zeta square by 20 equal to alpha by twice zeta. And then we basically from here we get 10, we transfer 10 to this side, 10 alpha by u infinity into zeta, and here ddx of delta zeta square by 20, if we differentiate, we get delta ddx of delta zeta square plus delta square, basically this delta into this delta square into ddx of zeta square. This equation 11 we get from here, where we can now, if we recall, substitute delta and delta t from basically velocity boundary layer solution, where if we recall, we got delta d delta dx equal to 140 by 13 nu by u infinity, and delta square equal to 280 by 13 nu x by u infinity. This we obtained while solving momentum integral equation. And if we substitute these two quantities in this, we'll get zeta cube plus twice x zeta ddx of zeta square 13 by 14 into 1 by Prandtl number. And it is a little involved to solve this equation. We again put another variable chi, which is equal to zeta cube. Then d chi dx is thrice zeta square d zeta dx, sorry, chi equal to zeta cube. Then d chi dx is 3 zeta square d zeta dx. And then if we substitute in equation 12, we will get chi plus 4x by 3 d chi dx equal to 13 by 14 1 by Prandtl number. We can rearrange this equation as d chi by dx plus 3 by 4x into chi equal to 13 by 14 1 by Prandtl number 3 by 4x. Just rearrange this, d chi by dx plus 3 by 4x into chi equal to 13 by 14 1 by PR 3 by 4x. This linear differential equation, for which we can solve this equation if we know the integrating factor, and we can very clearly see that integrating factor will be x power 3 by 4. So with the integrating factor, we multiply this equation x power 3 by 4 d chi dx plus 3 by 4x into chi x power 3 by 4 equal to 13 by 14 1 by Prandtl number 3 by 4 into basically x to the power 3 by 4, and we had 1x in the denominator, that will make x to the power minus 1 by 4. So we get a closed form expression ddx of x power 3 by 4 into chi from here. This is ddx of x power 3 by 4 into chi, these two together, equal to 39 by 56 1 by Prandtl number x to the power minus 1/4. And we can get from here chi equal to then 13 by 14, 1 by Prandtl number plus b obviously after integration this constant will come, because ddx of this expression we integrate it once, we get x to the power 3 by 4 into chi equal to this expression plus b. Then we write chi equal to this, from here we get 13 by 14, 1 by Prandtl number plus basically b into x to the power minus 3 by 4. B is the integration constant. After integration we get that, and then when we divide it by x to the power 3 by 4, we get b x to the power minus 3 by 4. B is the constant of integration. And so this is the equation, and the situation is we have both velocity boundary layer and thermal boundary layer. Now here we can consider a small unheated length from where the heating starts, beyond that heating starts, and the thermal boundary layer starts growing. So this is very small, the picture is magnified, the small distance, basically unheated initial length. So applying the boundary condition which has been described here, at x equal to x naught, delta t starts. So at x equal to x naught, we can say delta t equal to 0. And basically zeta equal to 0, because zeta is delta by delta t. Zeta is delta t by delta. So at x equal to x naught, delta t is 0. It starts from here. Delta t is 0. That means zeta is given by delta t by delta. Zeta is 0. So if zeta is 0, chi is also 0. So at x equal to x naught, chi is 0. We set this condition here. And from there, we get b. This integration, after this integration, we got this integration constant b. So b becomes basically minus 13 by 14, 1 by Prandtl number, x naught to the power 3 by 4. So when we get b, then we get the complete expression for chi. So chi becomes 13 by 14, 1 by Prandtl number minus 13 by 14, 1 by Prandtl number, x naught by x, because in the expression is b x to the power minus 3 by 4, and this x naught by x to the power 3 by 4. b into x naught to the power b x to the power minus 3 by 4. So this is b, and x to the power minus 3 by 4 we bring here. So this becomes the expression for chi, and chi equal to basically zeta cube. So, and zeta cube is basically we got from, if we remember, zeta is nothing but delta by delta t. So zeta cube is this. From here, if we try to find out an expression for zeta, we will get this. And zeta is nothing but delta t by delta. And delta t by delta equal to zeta. And then this entire quantity, we take the cube root, and that becomes 1 by 1.026, Prandtl number to the power minus 3 into 1 minus x naught by x to the power 3 by 4, entire quantity power 1/3. Now we introduce the concept of this unheated length, small unheated length, and under the limiting condition, this unheated length shrinks to 0. Then we can write delta T equal to basically delta by 1.026 Prandtl number to the power 1/3, because x naught shrinks to 0. So this becomes expression for delta T. Now, if we simply apply Newton's law of cooling, H, the heat transfer coefficient, TW minus T infinity is basically minus K. This is the thermal conductivity of the fluid into del T del Y at Y equal to 0. So, and del T del Y, we have already got this expression earlier, which is given by T infinity minus TW by delta T into 3 by 2. We can see while evaluating delta T. So, we are recapitulate that. So, minus K del T del Y is given by T infinity minus TW by delta T into 3 by 2, and TW minus T infinity comes from this side. Then this negative sign is taken care of in order to make this as TW minus T infinity, and we get H equal to K 3 by 2, and then basically minus K 3 by 2, TW minus T infinity gets cancelled out, and delta T 1 by delta T, and delta T is given by delta divided by 1.026 Prandtl number to the power 1/3. So this is so we substitute delta T as this in this expression, and then we in this expression also we have delta. Delta we substitute from the solution of momentum integral equation. So H equal to, we can see K 3 by 2, and delta is basically delta T into Prandtl number to the power minus 1/3. So delta goes to denominator, Prandtl number to the power minus 1/3, then becomes Prandtl number to the power 1/3, and delta further gets substituted by 4.64x into Reynolds number to the power half. So these are systematically, so we have to substitute one after another. Delta, we have to replace delta by this quantity, and then we have to delta T we have to replace by this quantity, delta by 1.026 Prandtl number to the power minus 1/3, and then we have to substitute delta by this quantity 4.64 into x divided by root over Reynolds number based on x, root over Rex. So if we do this, we will get this expression, and from this expression, if we can collect H, if we take x to other side and k to other side, we will get Hx by k, which is nothing but Nusselt number, and with little algebraic operation we will get these terms as 0.332 Reynolds number to the power half, Prandtl number to the power 1/3. So local Nusselt number, that is Nusselt number at any x from the leading edge, is given by 0.332 Reynolds number at that x to the power half into Prandtl number to the power 1/3. And this is quite similar to the expression that we obtained from, again, series solution, which was basically finally we called as Paulowson's solution. Now, in order to evaluate the average Nusselt number, we simply basically average heat transfer coefficient, that is given by 0 to L Hx dx integration divided by L, basically the length, and from there we can write HUL average, which is given by H average into L by K. And if we substitute Hx here from this expression, we will get 0.664 Reynolds number based on the plate length to the power half, Prandtl number to the power 1/3. Simply evaluating this integral and dividing by L, where Reynolds number based on plate length is given by rho U infinity L by mu. So this is average Nusselt number expression, this is local Nusselt number expression, and we can see the consistency between the numerical solution, exact solution which is obtained through the series solution, and the solution that we have just now found using momentum integral and energy integral method. Thank you very much for your interest. Thank you.